Our review today is going to be on vectors and matrices. Since I'm not there in class today, Monday we will do our conics review. So I kind of just flip-flopped Friday and Monday's plan. So here's the review on vectors and matrices, and then I think you have like 11 questions to finish in Canvas. But just kind of a reminder, a vector is a representation of both direction and magnitude. And so it is represented by a starting point and an end point, or an initial and terminal point. When we're looking at coming up with a representation of these 2 points, we had them in two forms. We had them in component form, and then we also had them in linear form that took the form of i's and j's. So a component form and a linear combination. And they're the same representation of the same vector. They just are in two different forms. So the way that we represent a vector or this movement upon the graph, you could graph these 2 points in Desmos and count. But what we want to do is find the distance between our initial x and our terminal x, and our initial y and our terminal y. And the way that we do that is we just do like x2 minus x1 and y2 minus y1. So if I was looking at the difference in these points, my x2 value is -5 minus my x1 value, which is a -7. And we know that two negatives make a positive. So -5 plus 7 gives me a distance of 2. And so the first component to either one of our forms is that 2. For my y's, my terminal y was 4. My initial y was 5. And so the distance between those is 1. And because it was going downward, that's where that negative came from, or the difference between 4 and 5 is a -1. So in both of these forms, you would represent that by saying 2, -1, or 2i and -1j. So when we write that, just kind of takes this form, and then you don't have to write the coefficient of 1, but if you wanted to, it would be right there. And like I said, a vector is both magnitude and direction. So you've already found the direction in which these 2 points moved, or the direction to go from your initial point to your terminal point. The last thing that you have to find is magnitude, or like the strength of that move. Magnitude is represented by a double set of bars. And so here it would be like the magnitude of CD. And the magnitude is simply, I'm going to write this, double bar of CD is the square root of the difference in your x's plus the difference in your y's. That's magnitude. So since we've already found the difference in our x values and the difference in our y values, we can plug that in. So the difference in our x's we said was 2, and the difference in our y's was a -1. And 2 squared is 4, and -1 squared is 1. So my magnitude is the square root of 5. That is my perfect value. But I think for us, we are good if we wanted to put this in a calculator and find your decimal. So I just opened up a Desmos screen here for a calculator. So my decimal would be the square root of 5, or my radical is the square root of 5. My decimal would be 2.2. So you could write the magnitude as the square root of 5, or you could write your magnitude as 2.2. So you're responsible for being able to give me both the component form and the linear combination, which if you know one, you know the other. You take those arrows off and you replace them with i's and j's, and then calculating that magnitude. You are not responsible for giving me the directional angle for any of these. So let's try another one here. I have an initial point where my x value is -1 and my y value is also -1. And this point is going to travel to 5, 3, and we need to be able to write that movement, that component form, that linear combination, and then we're going to calculate the strength of that move or the magnitude. So my x2 and my x1, my y2 and my y1, so finding the distance between those. So my x1 or my x2, which is my terminal, point, is 5 minus where I started, and for my y's is 3 minus -1. Two negatives make a positive. So my x had a movement of 6 and my y had a movement of 4. So in my component form, that's what's written with these arrows. So 6 and 4. Linear combination is written in i's and j's, so we're not having to do anything different. The only other thing we have to calculate is your magnitude. So your magnitude of this particular vector is equal to the square root of your change in x. So that triangle is just a shortcut for saying like x2 minus x1. It just means your change in your x's squared plus the change in your y's squared, so y2 minus y1. And we've already calculated those out. So the change in my x was 6. The change in my y was 4. 36, so 6 squared is 36. 4 squared is 16. If I add those together, I get a square root of 50. So the magnitude of my vector is equal to the square root of 50. If I wanted that as a decimal, then I can say the square root of 50 gives me 7.1. So the magnitude is about 7.1, and you do not have to tell me the directional angle. So this was one of the first things that we started off learning in the course because it was not too frightful. There wasn't a lot of math involved. So it's just kind of one of those things that get us comfortable. So let's look at some of those vector operations. So we are able to take different vectors and add, subtract, multiply, if we wanted to, all of those together. So direction is really important when you're looking at which you have to take away from which. So for example, I'm asked b minus a, which is not the same as a minus b. So just be very careful. So b is -3, 7. And I want to subtract from that vector a, which is 8, 0. So you just perform those foundational operations. So -3 minus 8 gives me a -11. And 7 minus 0 gives me 7. So my new vector is -3, 7. If you have to scale them up, like in example number 4, it is asking for 2 times the vector a plus 3 times the vector c. You have to scale them up before you can add them. So the product of 2 times vector a would be 16, 0, and the product of 3 and vector b would be 18 and -27. Now you have the ability to go in and add those together. So 16 plus 18 gives me 34, and 0 plus a -27 gives me -27. So that would be my new vector. You can even scale them with fractions, so you would treat the fractions the same way that we did with number 4. So you would just go in and multiply each one of those components with -1/3 for vector c, and then -5/2 for vector a, and then put those two together. So there are times when you're going to have to solve a system of equations. We did it in 2 methods. We did graphing, and then we did matrices, or building a matrix in the calculator. So I'm going to show you how to graph it first, and then I'm going to have to go over to my calculator and do the matrices. So we'll just do graphing first, and then we'll go into matrices. So graphing and solving by graphing is very simple, especially if you're using Desmos, because you can come in here, you can build your system completely in Desmos. So the first component of my system is y minus 2 squared is equal to 8 times x plus 4. You don't have to clean them up very often, if ever. So you have this like a hyperbola shape going on here, just one side of it. And the second part of your system is going to be the x plus 5. So x plus 5 squared plus y minus 2 squared is equal to 25. So the circle. And the solution to any system, no matter what, is where your two functions intersect. So I have two solutions here because I have two intersections. I have an intersection with the circle and the hyperbola at -2, 6. And I also have a solution at -2, -2. So if I was asked to solve each system by graphing, the solutions would be -2, 6 and -2, -2. So anytime it says solve, by graphing, I would just go straight to graphing. It's very basic. It's very simple. And it's not too complicated if you're just putting it in Desmos and you're looking where they intersect. Desmos also only graphs real solutions, so it will automatically take out any extraneous solutions that you need. But that's just graphing any system, nonlinear versus linear. And then you can also build them in, if you have more than two variables. So for example, if you have x, y, and z, you can build them in a matrix, but anytime it's just x's and y's, Desmos is going to be your go-to, especially for things like 33. So we don't have to do like elimination or anything like that. We can just always go by graphing. So if I wanted to look at number 33, I could take these two out and build my new function. So it looks like it's going to be the intersection of two quadratics or two parabolas, and negative y equals negative x squared minus 3x plus 11. So I have a green parabola and I have a blue parabola. Since they intersect twice, I have two solutions. Those solutions are -1, 7 and -7, 17. So those are pretty foundational. It gets a little crazier when you start looking at these three variables. You have x, you have y, you have z. These are a matrix because Desmos really graphs in just 2 dimensions. X, y, and z is more of a 3-dimensional thing. It's also got 3 different variables. So we do need to build a matrix. So in order to build a matrix on our calculator, we need to get into the matrix kind of mode. Matrix is written in blue right underneath the button that says math. So we're going to hit second and then that button. Here's going to be where all your matrices are stored. Here's the different things that you can do within your matrix. If you scroll to math, you can find all of those. The one that we're going to use most often is this RREF. It stands for reduced row echelon form, and we call it really, really easy form. But the first thing we need to do is edit. So we need to build this matrices. So it's going to ask for you for dimensions. The dimensions of any matrices are rows versus columns. So we currently have 1, 2, 3 rows, and we have 1, 2, 3, 4 different columns. So our matrices has the dimensions 3 by 4. So we're going to build it in the calculator, and it will automatically open up to the size you need. If it's not the size you need, you probably have written your numbers backwards. So we're going to come in here and we're going to start filling it in with coefficients only. So I look at my first row, the coefficients are -1, -2, 1, and then my final value is 10. My second row is 4, +3, +3, and my final value is 6. And my third row is 3, 4. I don't have a z value, so I need to keep it as 0, with my final total coming out to negative 11, so that your final things, everything on the right side of your equal sign, is lined up in that last column. Make sure you click enter so that it's stored. And in order to solve a matrices, you're going to go back to matrix, and you're going to look for reduced row echelon form, or we call it really, really easy form. So we're going to scroll to math, and we're going to go all the way down to where it says reduced row echelon form, or RREF. And it's going to ask you the reduced row echelon form of what? Well, my matrices was matrix A. That's where I put all my junk. So I go back, I pick matrix A. Now it's asking me if this is what I want. My answer is yes, so I click enter, and it gives me the following matrix. It gives me 1, 0, 0, 0, 1, 0, 0, 0, 1, negative 96, 72, and 58. The reason we like this is because this value represents X, Y, and Z. So it's saying 1X, 1Y, and 1Z. Their corresponding values are 96, 72, and 58. So if I asked you what is the solution to this system, the solution to this system is negative 96, 72, and 58. So let's do another one. We have another matrix here. It is a 3 variable matrix. So I know that my dimensions are 3 rows by 4 columns. So I'm going to come in to my matrix. I'm going to edit. I already have a 3 by 4. So all I'm going to do are change these numbers. So my coefficients are 5, 1, 1, and 14. Negative 4, negative 2, negative 2, and negative 24, negative 4, 4, 1, and negative 15. So I've built my matrix, and I'm going to look for the solution of that particular matrix. So I go quit or second mode, go back to your matrix, tell it that you're going to be doing some math, and you're going to use reduced row echelon, and your matrix was matrix A, so that's the matrix that we're going to use because we've edited our 3 by 4. And so this time your solutions are 0.67, 7.67, and 18.3. If they wanted them in fraction form, you'd have to change them into fraction form. So we could look at maybe going math and see if we can change our answers into fractions that way. It gives you your matrix as a fraction, and so you can either have decimals or you can give your answers in fractions: 2/3, negative 23/3, or 55/3. But that's how you're going to find the solution to a system of equation. Sometimes you're going to have a word problem and you're going to need to build a system of equations. You build the system of equations and use the matrices to solve.